The moon's dusty surface will soon feel American boots again. NASA's Artemis program represents America's boldest lunar endeavor since Apollo. This new chapter in space exploration combines government vision with private sector innovation. SpaceX's Starship lunar lander stands ready to revolutionize moon transportation. Blue Origin's Blue Moon lander brings cutting-edge technology to the mission. These competing systems ensure redundancy and drive technological advancement. The lunar South Pole holds the key to sustainable presence. Scientists estimate billions of gallons of water ice hide in shadowed craters. This frozen treasure could transform space exploration economics. Water molecules can be split into hydrogen for fuel and oxygen for breathing. The moon could become the solar system's first interplanetary gas station. NASA's Gateway Lunar Station will serve as a crucial waypoint. This orbiting outpost will host astronauts before their descent to the surface. Gateway's modular design allows for future expansion and specialization. The European Space Agency contributes the habitation and logistics outpost module. Canada's advanced robotic arm system will perform delicate operations. Japan's life support technologies ensure crew safety during extended missions. International cooperation spreads costs and shares expertise across nations. China's ambitious lunar program presents both competition and potential collaboration. Their Chang'e missions have already demonstrated impressive capabilities. Russia's renewed lunar interest adds another dimension to the space race. India's successful Chandrayaan-3 landing proved their emerging space power status. Commercial space companies are disrupting traditional exploration models. SpaceX's Starship can deliver massive payloads at unprecedented low costs. Blue Origin focuses on precision landing technology for targeted operations. Dynetics offers alternative approaches through their human landing system design. The technical challenges of lunar settlement are daunting but solvable. Lunar regolith poses unique dangers to equipment and human health. These razor-sharp dust particles require innovative mitigation strategies. Radiation exposure demands new shielding materials and protective protocols. Extreme temperature swings test the limits of material science. NASA's next-generation XEMU spacesuit addresses Apollo-era limitations. Enhanced mobility allows astronauts to work more effectively on the surface. Improved dust resistance protects both suits and habitat interiors. The Artemis program makes history through its crew selection. The first woman on the moon will inspire generations to come. Diverse astronaut selection reflects America's multicultural society. Scientific exploration drives the mission's core objectives. Lunar geology holds clues to Earth's early history. The moon's pristine surface records billions of years of solar system events. Radio telescopes on the far side could revolutionize astronomy. Protected from Earth's radio noise, they'll peer deeper into the cosmos. Biological experiments will study long-term effects of partial gravity. These findings are crucial for future Mars missions. The lunar economy presents extraordinary potential. Helium-3 deposits could power future fusion reactors. Rare earth elements are abundant in certain lunar regions. Space tourism may emerge as a viable industry within decades. Legal frameworks evolve to accommodate new space activities. The Artemis Accords establish norms for peaceful lunar exploration. Over 30 nations have joined this growing coalition. These agreements prevent territorial claims while encouraging cooperation. Technology demonstrations validate critical systems before crewed missions. The Capstone mission tested a unique near-rectilinear halo orbit. Lunar flashlights searched for surface ice using innovative instrumentation. The upcoming Viper rover will map water resources in detail. Commercial lunar payload services accelerate surface operations development. Astronaut training intensifies as launch dates approach. Field geology exercises in volcanic regions simulate lunar conditions. Neutral buoyancy laboratories perfect extravehicular activity techniques. Virtual reality systems prepare crews for actual lunar landmarks. The Space Launch System represents NASA's most powerful rocket ever. Its successful Artemis I mission proved the design's capabilities. Orion spacecraft provide crew transportation beyond Earth orbit. Advanced life support systems recycle vital resources efficiently. Closed-loop environmental control minimizes resupply requirements. Solar power systems provide reliable energy for surface operations. Nuclear power options offer advantages for permanent bases. Surface habitats must withstand extreme environmental challenges. Inflatable modules provide spacious living quarters when deployed. 3D printing technology could utilize lunar regolith as construction material. Robotic precursors perform essential reconnaissance missions. These autonomous systems scout landing sites and resources. Automated construction equipment may prepare landing pads and foundations. The first Artemis landing will target the lunar South Pole. This strategically important region contains permanently shadowed areas. Ancient water ice preserves a record of solar system history. Nearby sunlit peaks offer ideal locations for solar arrays. Initial surface missions will last about 1 week. Later expeditions will extend to several months' duration. Rotating crews will maintain continuous human presence. Scientific investigations will prioritize sample collection. Deep drill cores could access primordial lunar material. Seismic networks will monitor moonquake activity. Astrobiology experiments will test life's limits in alien environments. In situ resource utilization demonstrations prove sustainability concepts. Oxygen extraction from regolith is particularly promising. Metallic components could be refined for local manufacturing. Additive manufacturing tests will assess lunar construction techniques. Cultural considerations play an important role in lunar exploration. The moon holds sacred significance for many Earth cultures. Native American advisors help shape respectful exploration policies. Historic Apollo sites receive special protection as heritage locations. Educational outreach inspires future generations of explorers. STEM programs connect classrooms with active missions. Art competitions engage creative minds across disciplines. Virtual reality experiences bring the moon to Earth. The lunar return represents just the first step. Moon experience directly enables future Mars missions. Lunar gravity assists deep space transportation systems. Lagrange points could host way stations for interplanetary travel. Space-based industries may emerge within our lifetime. Public-private partnerships accelerate technological progress. NASA's commercial procurement model reduces taxpayer costs. Private companies assume development risks and reap rewards. This approach drives innovation at unprecedented speed. Competition between providers lowers costs dramatically. Safety remains the absolute highest priority. Redundant systems protect against single-point failures. Emergency protocols cover all conceivable scenarios. Medical contingencies are thoroughly rehearsed. Psychological support systems maintain crew well-being. International collaboration multiplies mission success chances. Global expertise combines to solve complex problems. Standardized interfaces enable seamless cooperation. Space diplomacy builds bridges between nations. The mission timeline progresses steadily forward. Artemis I successfully tested the complete spacecraft system. Artemis II will carry astronauts on a lunar flyby. Artemis III achieves the historic return landing. Subsequent missions expand the lunar foothold. Each accomplishment builds toward permanence. The long-term vision stretches decades ahead. Lunar industries may eventually employ thousands. Scientific discoveries could rewrite physics textbooks. Human culture will expand beyond our home planet. The moon represents humanity's first step into the cosmos. Section 2, Challenges and Opportunities. Radiation protection remains one of the toughest challenges. The lunar surface lacks Earth's protective magnetic field. Solar particle events deliver dangerous radiation bursts. Galactic cosmic rays present constant background radiation. Water-filled walls provide effective shielding against particles. Underground lava tubes offer natural radiation shelters. Active magnetic field concepts are under development. Pharmaceutical countermeasures may reduce biological damage. Nutritional supplements could boost cellular repair. Gene therapy research explores radical protection methods. Lunar dust presents unique engineering problems. Regolith particles damage mechanical components through abrasion. Electrostatic charging causes problematic dust adhesion. Nanoscale coatings reduce surface friction and sticking. Multi-stage airlocks minimize dust transfer into habitats. Magnetic filtration systems trap airborne particles effectively. Next-generation spacesuits incorporate advanced dust mitigation. Thermal management requires innovative solutions. 2-week lunar days create prolonged heating. Equally long nights bring extreme cold. Heat rejection systems must operate efficiently. Energy storage systems require massive capacity. Compact nuclear reactors provide steady power. Regolith insulation stabilizes habitat temperatures. Specialized radiators function in vacuum conditions. Communication systems need robust architecture. Direct Earth visibility is periodically blocked. Lunar orbit relays ensure constant connectivity. Delay-tolerant networking handles signal interruptions. Laser communications offer high-bandwidth alternatives. Navigation systems adapt to lunar conditions. Traditional GPS doesn't function on the moon. Celestial navigation provides backup positioning. Terrain relative navigation guides precise landings. Beacon networks enable surface localization. Human factors present complex challenges. Isolation affects crew psychology over time. Confined living spaces test interpersonal dynamics. Extended mission durations require careful planning. Virtual reality systems provide Earth connections. Private quarters preserve individual space. Crew selection balances skills and personalities. Medical capabilities must be comprehensive. Trauma care requires automated systems. Earth-based specialists assist via telemedicine. 3D printers produce custom medical tools. Emergency evacuation plans cover contingencies. Robotic surgical systems may be included. Stabilized pharmaceuticals have extended viability. Food systems balance nutrition and morale. Hydroponic gardens provide fresh produce. Prepackaged meals offer dietary variety. Culinary creativity maintains crew well-being. Waste recycling achieves near-closed loops. Water recovery systems exceed 90% efficiency. Air revitalization removes carbon dioxide. Advanced systems convert CO2 to oxygen. Urine recycling produces potable water. Solid waste may fertilize hydroponic systems. Economic models ensure long-term viability. Government funding jumpstarts development. Private enterprise drives scalability. Space tourism could generate significant revenue. Research facilities attract commercial partners. Media rights create additional value streams. Lunar mining remains speculative but promising. Technology demonstrations prove extraction methods. Market forces will determine ultimate viability. Legal frameworks must evolve rapidly. Property rights lack clear precedents. Resource utilization requires new guidelines. Safety regulations protect all participants. Dispute resolution mechanisms are essential. Insurance models adapt to space risks. International treaties evolve slowly. National laws fill immediate gaps. Enforcement mechanisms remain undefined. Diplomatic channels prevent conflicts. Scientific exploration drives mission priorities. Lunar geology reveals solar system origins. Radio astronomy benefits from quiet far side. Fundamental physics experiments test theories. Biological studies examine adaptation. Artistic interpretations expand perspectives. Cultural heritage is preserved. Indigenous knowledge informs practices. Global narratives emerge. Ethical considerations guide decisions. Planetary protection prevents contamination. Archaeological sites are documented. Environmental impact is minimized. Inclusivity ensures broad benefits. The long-term vision inspires. Moon bases could house hundreds. Research outposts expand knowledge. Industrial activities may follow. Launch facilities enable deeper exploration. Fuel depots support solar system travel. The moon anchors space infrastructure. Humanity becomes multiplanetary. Perspective shifts fundamentally. Earth appears fragile from lunar distance. Cooperation replaces competition. Challenges unite nations. Knowledge benefits all. The next decade proves critical. Artemis lays the foundation. Private sector adds capabilities. International partners contribute. Public support sustains funding. Each mission builds momentum. Failures provide lessons. Successes attract investment. Technology matures rapidly. Costs decrease over time. Safety improves with experience. The moon becomes familiar. Mars grows nearer. Human destiny expands. The universe beckons. Expansion additions. New propulsion technologies could reduce Earth-Moon transit time. Plasma rockets may cut the journey to just 3 days. Advanced composites enable lighter spacecraft structures. Self-healing materials repair micrometeoroid damage automatically. Artificial intelligence manages complex life support systems. Machine learning optimizes resource allocation in real time. Autonomous robots perform dangerous surface operations. Swarm robotics could construct entire bases before human arrival. Quantum communication enables secure Earth-Moon data links. Entanglement-based systems offer hack-proof transmissions. Biotechnology may enhance human radiation resistance. Gene editing could create space-adapted organisms. Tissue engineering grows replacement organs for long-duration crews. Nanotechnology provides microscopic repair systems. Molecular machines maintain habitat integrity. Smart dust sensors monitor environmental conditions. Virtual reality training evolves with haptic feedback. Neural interfaces allow direct machine control. Brain-computer connections enhance astronaut capabilities. Exoskeletons augment strength for surface labor. Powered suits enable heavy lifting in low gravity. Energy storage breakthroughs transform surface power. Solid-state batteries offer safer, denser storage. Superconducting systems minimize transmission losses. Food production achieves near-complete closure. Insect farms provide efficient protein sources. Algae bioreactors recycle waste into nutrients. Closed ecosystems test planetary colonization concepts. Medical diagnostics reach new sophistication. Lab-on-a-chip devices perform complex analyses. Non-invasive scanners detect health changes instantly. Stem cell treatments regenerate damaged tissue. Space construction techniques revolutionize engineering. In-orbit assembly creates massive structures. Regolith sintering builds radiation shelters. Telerobotics allows Earth-based experts to assist. Cultural exchange programs enrich lunar society. Art installations reflect human creativity. Performance spaces maintain Earth traditions. Educational programs connect lunar and terrestrial students. Economic models diversify beyond government funding. Space-based manufacturing exploits microgravity. Pharmaceutical production benefits from pure crystals. Semiconductor fabrication achieves new quality standards. Tourism expands beyond government astronauts. Lunar hotels offer once-in-a-lifetime experiences. Low-gravity sports create new entertainment forms. Scientific tourism attracts researcher visitors. Environmental protection gains importance. Planetary parks preserve pristine areas. Impact monitoring tracks human influence. Sustainability becomes core to operations. Waste management achieves near-zero discharge. International cooperation deepens over time. Joint missions share costs and rewards. Cultural understanding grows through collaboration. Peaceful exploration sets precedent for Mars. The moon becomes humanity's stepping stone. Lunar experience directly enables Martian settlement. Technologies proven on the moon transfer to Mars. Operational experience informs longer missions. Psychological understanding prepares for isolation. Medical knowledge protects against new challenges. The moon becomes a classroom for planets. Humanity's future stretches toward the stars. Earth's companion becomes our first off-world home. Generations will remember this historic transition. The moon landing was just the beginning. Permanent expansion changes human destiny. Our species becomes inherently spacefaring. Civilization extends beyond terrestrial limits. The universe becomes our shared heritage. Exploration defines our collective future. The next chapter begins now. America leads this historic endeavor. The world joins in common purpose. Together we return to the moon. This time to stay, to learn, to grow, to prosper. The stars await,